Hello, my name is John Butler III, and I am doing my second video for Math 1000 Challenge video for 2016. We were posed with three questions, two of them, actually, all of them involving some form of the limit, since that is was the main topic of our section this week, so I'm going to dive into that. But the first thing I want to do before explaining this problem is explain a simple concept. That the limit as theta approaches 0 in sine theta over theta is 1. However, that also means that theta over sine theta is also equal to 1. The limit to that is also equal to 1. But why is that? Well, sine of theta when it's 0 equals 0, and when you make when you make sine theta equal to 0 is also 0. Thus, they're reversible since they equal the exact same thing on the top and the bottom. And because these two expressions equal the same thing, it is valid to say that that the function can be flipped. Therefore, we can apply this method into this problem. The first problem says, what is the limit as x approaches 0 of sine of 5x over sine of 4x? So the first thing that we will want to do is to actually separate this into two different equations multiplied by each other. So the sine of 5 over x over some variable times sine of 4 over x over something will equal what you want to do. So when you do this, you want to make this look exactly like this. So in this case, theta, which is 5 over x, is what you want to put in the bottom. And to get this to be so, to make it equal the same thing, you multiply by 5x. However, as you'll see later, you can actually take this x and put it right here instead of putting it on the outside, which will save you actually a lot of time. So, when you put the x on the right here, then you just multiply by 4 on the top, and then you divide by 4 on the bottom. And so when you do that, you get sine of 5x over 5x, the limit as x approaches 0 of sine of 5x over 5x times 4x over sine of 4x times 5 over 4, and both of these equal as x approaches 0, they both equal 1 times 5 over 4, so 1 times 5 over 4 equals 5 over 4. The second problem that he posed to us was number 28. This says, as the limit approaches infinity, of 2 plus squared plus the root of x over 2 minus the root of x. And so if you plug in infinity into these problems, although infinity is not a number, you can see that 2 plus the square root of infinity over 2 minus the square root of infinity is the same as saying any number plus infinity is infinity. So we can actually cross these numbers out. So we can say infinity over negative infinity. And so now that we have infinity over negative infinity, that is equal to negative 1, as you can see. And the reason how I got from here to here, when you take the square root of infinity, a square root of any number is a certain number. However, if that number gets arbitrarily bigger, that means the square root of that number also gets arbitrarily bigger. Therefore, the square root of infinity is also infinity. So that's why 2 plus infinity over 2 minus infinity is the same thing as saying infinity over negative infinity, and that equals negative 1. The last question is one that we just went over in class. Well, not just went over in class, however, we did just go over questions that dealt with this. So now that we're trying to find the derivative of a certain function in class, we're using the limit process to find said limit. So if you find where f prime of x equals the root of x at x equals 1 by taking the limit. So what does this mean in the forefront? Well, if we say that if we have this is not the same graph as this, but this is an arbitrary graph. So if we had a graph like this, and we take the slope as x and we give two lines, x plus x is over here, plus some interval, some arbitrary interval, and that will equal x plus that arbitrary interval value. So x, and then that would be x plus h, the function of x plus h. However, as we make h get arbitrarily closer and closer to 0, x plus h will equal x. So, and as we move that over and over, the slope of that line will change, because from here to here, that's the secant line that passes through this function. However, as we continuously get closer and closer to it, we get closer and closer to the slope at x, as the limit of h, which is this number, gets closer to 0. And so if we find the limit as h approaches 0, we can actually find the slope of the line that is tangent to the graph at x. So that's why we say the limit of h as h approaches 0, and we use this function because, like we said, f of h minus f of x over h. So so our function is square root of x. Therefore, we plug this number in, we plug this value into there, and we plug this value into there. So that comes to equal x plus h, the root of that, minus the root of x over h. And I just wrote it again right here. And then now, in order to get, because if we take the limit now, it will not exist at 0. The limit will exist at 0, but it will not be approaching a certain value because the limit will be over 0, and that's undefined. Therefore, if we want to multiply by the conjugate of the top. And so once we do that, it'll be, because a minus b times a plus b equals a squared minus b squared. So when we do that, we get x plus h without the root minus x without the root over h times the square root of x plus h root plus the root of x. So when we do that, the x actually cancels. So x minus x cancels out. And so then we get h over that quantity. However, h and h also cancels out. So then we have the limit as h of 0 approaches, as h approaches 0, is 1 over x plus h plus the square root of x. And so once we put that 0 in, we actually get 1 over the square root of x plus the square root of x. And then we get 1 over the 2 square root of x. However, we're not done. See, this equation is just the equation to get the tangent line, is the equation of the tangent line at any point on the function square root of x. So this is the function to get any point. We wouldn't do it at 1. And what we need to remember is that when you plug 1 in, y equals 1. So this is x of 1. This is x1. This is y1, as you see right here. So now we plug x into there, and the slope at x equals 1 is 1 over 2. So now we plug this into the y minus y1 equals m times x minus x1. As you see, that is the point slope form, so we can find the actual line, which this always gives you just a plain line. So once we plug our numbers in, y1 is 1 and x1 is 1. So y minus 1 equals 1/2 of x minus 1. And we do not have to simplify this term because this is actual line. So we are here. And that's problem C.